All right, ladies and gentlemen, what we will be talking about today are rational functions. Now, a rational function is related to material that was covered earlier in this course with rational equations. And if you remember, a rational equation was an equation that we were trying to solve where the variable that we were trying to solve for was in the denominator of a fraction. Well, a rational function is pretty much the same thing. It is a function, it's a collection of inputs and outputs, where we are trying to identify something, or where the variable that we would consider our input variable, typically x, is going to be in the bottom part of a fraction. So here, what you see on this screen is a very general kind of explanation about what a rational function is going to look like. A rational function is typically made up of different types of polynomials, where you will have a polynomial in the numerator and a polynomial in the denominator. And you don't always have to have a polynomial in the numerator. You could just have a number. But for a function to be considered a rational function, there must be some type of polynomial in the denominator, so that way we have our variable in the bottom of our fraction. Now, at the bottom here where it says the domain is all real numbers, well, it's all real numbers except for anything that would give me a 0 in the denominator, because as we've discussed again previously with rational equations, if I happen to have a 0 in the denominator of any fraction, that causes whatever we're talking about to become undefined, because what we're essentially trying to say at that point is we're trying to take a number and divide it by 0, which is not possible. So the domain of a rational function is going to be every real number except the numbers that would give us a 0 in the denominator. Now there are going to be two basic types of rational functions. The first one that you see here is what most people typically think of as a rational function, where we just say it is 1 over x. Now again, as I said a second ago, the numerator generally in a rational function will be a polynomial of some type, but it does not have to be. So as you see in this most basic function, the parent function, the numerator is just a number. It's just 1. So it doesn't have to have a polynomial in the numerator, but for it to be rational, we have to have something in the denominator that's x. So that's where the polynomial in the denominator comes into. The second basic parent function, rational functions that actually have two parent functions, is one of the things that's a little bit unique about them, is that this one has what we refer to as the reciprocal squared function, where we have 1 over x squared, and this is basically what it looks like. Now, one of the things that we're seeing in both of the uh, basic types of rational functions that we have here is that they have a little bit of separation to them where things are not going to be used, and they're what we would generally refer to approaching a limit of some kind. Now, as you look at this particular function, the curve on the right and the curve on the left both approach certain variables or certain values. At the x-axis going across, you see the curve coming down to the right or the curve coming up to the left. What we would say those approach a number, but they don't generally get to become that number. This would be referred to as an asymptote. An asymptote is simply a, when a function behaves where it will approach a value but doesn't get to be that value. So because this is an asymptote that creates a horizontal line, we would call it a horizontal asymptote. Now, horizontal asymptotes, as we go further into rational functions, they're going to play a role as far as where we want to identify where they are, so that way we can graph them. And one of the things that we'll also recognize is that horizontal asymptotes can actually be crossed. Now here, if you're looking again at the function as it curves up or it curves down, they approach the y-axis. So this would be referred to as a vertical asymptote. Now, a vertical asymptote and a horizontal asymptote, generally speaking, are the same, except for the direction that the lines go. A horizontal asymptote can be crossed by a function. A vertical asymptote, however, can never be crossed by a function because that is the point where a function becomes undefined. In order for me to have a vertical asymptote when y is equal to 0, well, I'm sorry, when x is equal to 0, that's the point where I would have to have 0 in the denominator of a function. And that's where a vertical asymptote would be generated. So vertical asymptotes, those are the numbers of our domain that can't be used, and vertical asymptotes can never, ever, ever be crossed by a function, whereas horizontal asymptotes can. And we would kind of see the same thing here. Because of the reciprocal squared function, what we would see, again, we have a horizontal asymptote where y is equal to 0, and a vertical asymptote where x is equal to 0, and those are, again, horizontal asymptotes are generally something we don't always cross, but we can cross. Vertical asymptotes can never be crossed by a function. Now, one of the things that we're going to be discussing with rational functions, similar to other functions that we've been discussing, is how does its end behavior look? Meaning, as x approaches a positive infinity or a negative infinity, what does y do? And this is notation that we've been using in class, so it should be relatively familiar to you. And we are going to be, again, employing it just like what we did with polynomial functions, meaning as x goes to the left forever, or as x goes to the right forever, how does y behave? Now, the difference between a rational function and a polynomial function is that with polynomial functions, typically, as x approached one extreme or another, meaning positive infinity or negative infinity, y would also approach either a positive infinity or a negative infinity. Well, with a rational function, it's a little bit different. Generally speaking, as x approaches an extreme, one way or the other, y will no longer go to a positive or negative infinity. A lot of times we're going to have horizontal asymptotes, and as a result, y will not approach an extreme, rather it will approach a particular number. And that is, again, is the asymptotes where we approach a particular number, that is kind of something that we would actually refer to as a limit, meaning as x approaches some extreme, y approaches some particular value, and so we would refer to that is the limit of the function. Now here, this is a new set of notation. This is another thing that we're going to be working with rational functions, and it's still kind of talking about in behavior, but it's a little bit different. Meaning, because we can have a vertical asymptote, meaning there's something that's making the function undefined at a certain point, we want to know, well, how does the function behave as it approaches that particular asymptote? Now, let me explain what this notation, how you read it. It's similar to what we had before, meaning as x approaches some value, but instead of approaching an extreme value, either positive or negative infinity, it's approaching a particular number. So c in this case, c is just going to represent a number of some kind, whether it's a 5 or a -2 or whatever the case may be. Now what you're seeing here and here, that is an indication of where the function is approaching that number from. So let's just say that x is approaching some number. The negative symbol on the c, whatever the number happens to be, it says as x approaches c, what we're going to say, looking at the negative sign on the superscript portion of the c, is the way that we would read that is we would say as x approaches c from the left side of the graph. And the plus sign would say as x approaches c from the right side of the graph. So let's just say that we had our reciprocal parent function, something like this. The c in this case would be when x is 0. So we would say as x approaches 0 from the left side, and so we would say, what does x do as it comes to that vertical asymptote from the left side? And here we would say, as x approaches 0 from the right side, what does y do? That's basically what the function, or what this notation is asking you to understand. Instead of going to the left forever, to the right forever, to an extreme, instead we're kind of coming inwards from the left side or the right side, approaching a particular number, and then evaluating what does y do. So let's take a look and see how we're going to use those particular notations. So here we have a function that has been graphed for us. Now, the transformations that we've discussed for every other function still apply to rational functions. Where it says x plus 3 in parentheses, that is simply saying take the parent function and move it to the left 3 spaces. Where it says plus 2 on the right side of the fraction, that's simply saying take the parent function and translate it up 2 spaces. So the function that you're seeing on the screen here is the parent function that has been shifted 3 spaces to the left and 2 spaces up. That's all the transformations are telling you to do here. Now, as we look at the graph, we see that we have a horizontal asymptote here when y is equal to a positive 2. That's what the 2 on the transformation of the equation tells us. Well, the positive 3 says, where it says x plus 3, that says move it 3 spaces to the left. So that's where my vertical asymptote is going to be located, because if we substitute a negative 3 in for x, that would give us a 0 in the denominator. So here my vertical asymptote is located at x is equal to 0. So here, oops, I'm sorry, I'm not paying attention. X is equal to negative 3. So in the instructions up at the top, it says, explain what's happening as x approaches these values. Okay, so in this case, positive or negative infinity and negative 3. So let's look at the one that we're most familiar with first, meaning as x goes to the left side forever to negative infinity, what does y do? Now you can see, following the function up, as x goes further and further to the left, y gets closer and closer and closer to that 2. So y is simply going to approach a positive 2 in this case. And if we go in the other direction, as x goes to the right side forever to positive infinity, you can see, following the graph down, it's just going to get closer and closer and closer to the positive 2. It doesn't go to an extreme anymore. And all we're doing is just looking at the graph and following its curve and saying, oh, well, as x goes to the left forever or to the right forever, both sides approach the same number, positive 2. That's what the horizontal asymptote does. Now let's look at our new notation. So here, where it says as x approaches 3 and kind of in that exponent spot with the negative sign, 3 negative, what this is saying as, excuse me, as x approaches 3 from the left side, what does y do? Okay, let me pick a different color here so we can differentiate what we're looking at here. Give me something that looks a little show up. Okay. So here, what we're talking about, as x approaches the number negative 3 from the left side. So this is as x approaches negative 3 from the left side. And this should be a negative 3 here and a negative 3 here. What does y do? Well, you can see as x comes from the left side to the right side, heading towards the negative 3, it's going to curve down and down and down. And it continues going down and down and down to negative infinity. And so here, where it says negative 3 plus, meaning it goes to the from the right side, okay? So we're looking at it this way. As x comes to the negative 3 from the left side of the graph, moving in, it's coming in from the right side to the left side here as x approaches negative 3 from the right side. What does y do? Well, following the curve, it's going to go up and up and up to a positive infinity, and that's how we would write our notation. So looking here, same exact thing. Now, in the function, the parent function that we would have here would simply be y is equal to 1 over x squared. This is the reciprocal squared function. And I know that 1 because of the way the graph looks, but 2 because of the multiplicity of the factor in the denominator being a 2. So let's look at this one. See how it goes. So as x approaches, and the transformations that we would see from the parent function in the function that we have now, in the numerator where it says -1, that's simply saying take the parent function and reflect it over the x-axis. In the denominator where it says x minus 2, again, that would refer to a horizontal shift 2 spaces to the right, and the +1 would simply say move everything up 1 space. And so that's what would produce the function that you see here. Now looking at our notation, we're going to say as x approaches positive infinity, meaning as x goes this way forever towards positive infinity, what number does y approach? Well, in this case, the horizontal asymptote is at y is equal to 0. So as x approaches a positive infinity, y heads towards 0. And the other direction, as x heads towards negative infinity, again, y is going to approach the same number, the horizontal asymptote, y is equal to 0. So now we're looking at our new one. We have a vertical asymptote here at x is equal to positive 2. So the notation, and let me go to a different color here to differentiate. Here what it's saying, as x approaches positive 2 from the left side, and as x approaches positive 2 from the right side, what direction does y go? And you can see in both of them, they're going to head down to a negative infinity. Now here, what it's asking you to do, a very similar type of expression, or a very similar type of skill that we practiced before, is what is the transformations that occurred to produce the graph that you see here. So the parent function that produces something that looks like this is 1 over x squared, the reciprocal squared function. So we want to know, okay, here's my vertical asymptote here at x is equal to -2. And I have a horizontal asymptote here at y is equal to -2. And we want to know what transformations did occur in order for us to produce this thing. Now, let me just address this last part right here, because this is just kind of something that they're adding on as a technicality thing, saying, okay, when we do our transformations, okay, we could do horizontal shifting, vertical shifting, we could do reflections across the x or the y axis, but we could also do a vertical or a horizontal stretch. Well, here what it's saying is that a being equal to 1, basically what it's telling you is that there's no vertical stretch. So what the function that we're seeing here is essentially it's just asking you to say, okay, take the parent function and write the transformations that you're seeing here, which are essentially going to be translations to the left and down. So to go from the parent function to what we have here, we're going to say 1 over, and we'll put it in parentheses. So we're moving 2 spaces to the left, so I'll say x plus 2, and I'll close the parentheses squared, and because we're moving 2 spaces down, we'll say minus 2, and that would be the end of that particular transformation. So here, what we would see here, when they go in opposite directions, this is just the reciprocal function, 1 over x. Now the graph of this one goes like this. And you can see in the graph that we have here that what's on top and what's on bottom are going in opposite directions of the parent function. So what that lets me know is that the numerator has a negative sign on it because it has been reflected across the x-axis. So here I want to see where my horizontal and my vertical asymptotes and compare it to the original one. So the horizontal and vertical asymptotes of the parent function cross at the origin. Okay, so from the origin to this point here, I moved one space to the right and three spaces up. So to show the side-to-side shift, one space to the left, I will say x minus 1 in the denominator and plus 3 for the shift up. And that is essentially all the skills that we're going to be talking about here for rational parent functions. One of the things that we're going to be moving on to next is a process for how we graph them from an equation, but that'll be something that we'll tackle in our next video. So again, basically what we wanted to know here is looking at the notation as far as how a function behaves as it approaches an asymptote of one kind or another, and can we identify transformations in a given graph based off of the function that we see from the parent function. So guys, I hope you learned something here. If you had any questions, please make sure you write them down and bring them to me to address them in class, and we'll see you guys soon.